We start with the new topic, which is one of the leftover topics from class 11, which is wave mechanics. We were doing geometrical optics before this, and just to clarify a point, your upcoming test on 28th will have only geometrical optics from this track. There was a suggestion earlier to include part of wave mechanics, but since we have having only one lecture today before the test on 28th, so no part of wave mechanics will be included in that in this particular test. Okay. Right. So starting with wave mechanics. So let us understand what a wave phenomena is. First of all, okay. So let us understand waves, or what we call any wave phenomena. So if we look in our everyday lives, there are a lot of examples of wave phenomena, which are clearly different in how the system progresses, or what takes place in terms of interaction physically within the system in a wave phenomena, as opposed to let's say something like a particle phenomena, or a phenomena related to rigid body mechanics or rigid body motion, etc. There's a clear demarcation between the two, and let's understand with this with some examples with respect to this. So, for example, if we take the situation of, let's take something quite abstract, like, we take the example of communication via email. Okay. Versus by post, which is the normal mail, the normal system of mail, letter, etc. Or we take something more easy to understand. Let's say something like sound propagating versus, let us say something like electric current. Okay. Now, if we look at these kind of examples, we'll understand that everything which I'm comparing, it involves transmission of information or transmission of energy. Okay. But in the case of, for example, something like email, what is happening is the transmission of information is happening without any physical transportation of particles. Okay. In email, there is no transportation of any particles, whereas in a mail or a letter, or by post, what is happening, there is matter which is transported. It's actual physical matter which is transported from one point to another. Even in sound, if you think about it, sound you can think not only in terms of information, but in terms of energy. Okay. There is energy propagated. Okay. Without particles transported from one point to another. So, for example, when I'm speaking, okay, and somebody is standing a bit far away from me, but listening to the sound waves directly and therefore getting information from me, there's actual transmission of energy from right from my vocal cords right up to the eardrum of that person. There is mechanical energy that is getting propagated, but there are no physical particles that are moving all the way from here to there. Yes, physical particles are involved. For example, there is vibration, or there is oscillation of the air particles which is happening as a result of the sound waves propagating. But you can say with confidence that actual particles which are disturbed by my vocal cords vibrating back and forth, those particles are not displacing all the way and reaching that other person's, that listener's eardrums. Okay. They are vibrating only in place, and another set of particles around them are vibrating in place. Another set of particles around them are vibrating in space. And like that, ultimately there is some kind of vibrational mechanical energy that is reaching the eardrum of the listener. And as a result of that, both energy and information is propagated. But actual physical particles are not transported all the way from the source to the receiver of the waves or receiver of that information. Whereas in the electric current, for example, you know that electrons get transferred. So there is electrical energy which is propagated, but physical particles or matter is actually transported, okay, from one point to another. So this is the difference between any wave phenomena versus any non-wave phenomena. So the broad description of waves, okay, you can say the broadest description of a wave phenomena is that it is a physical phenomena or it's a set of physical phenomena in which energy or through energy information is propagated, but such that no physical matter as such propagates from the source to the receiver. Any phenomena which you can think where this is happening will come under the category of wave phenomena, however abstracted it or however everyday it is. So for example, you have waves on a string. It's very obvious that if you mark any point on the string with a pen or something, you will see that that point doesn't physically move along the string. That point only goes up and down. Whereas you can see that the energy which is propagating when you send a vibration through the string is propagating along the length of the string. So you can see immediately what's happening, what we're talking about. That energy is propagating along the string, but the particles are not moving in the same way the energy is moving. Or they are not going from the source of the pulse to the receiver at the other end of the string. Okay, so it's very obvious, this one. Then obviously sound waves, then waves on the surface of a liquid. These are all very easy to understand examples, but somewhat more abstract examples are, for example, any sort of electromagnetic waves. So radio waves, infrared, visible light, microwaves, which are responsible for creating heat also by creating vibration in molecules, X-rays, ultraviolet, gamma radiation. These are all examples of what come under the category of electromagnetic waves. In fact, whereas these were examples of what is called mechanical waves. So we'll come to that demarcation also. But electromagnetic waves are ones where electromagnetic energy propagates, whereas mechanical ones are ones in which mechanical energy propagates. But they both come under the broad description of waves. Okay. And now there are the more abstract examples like the email communication I told you about, or when you send, for example, there is Mexican waves in crowds. A Mexican wave created in a crowd of people. Okay. Something which we can only happily imagine right now because of the current situation in the world, in a stadium. So what happens in this is that you have some kind of a disturbance or a pattern of people alternately sitting and standing. So what you see is that, there are people sitting everywhere, and then few people who are standing up, and rest of the people sitting. Now this disturbance or this pattern travels. So alternately now these people sit down, and the people next to them, they stand. Then after a while in the crowd, more people are sitting, Now more people here are standing. So you see that this disturbance is traveling. But do you see people running around the stadium in the direction in which the disturbance is traveling? No. The disturbance is traveling in this direction. People are only standing up and sitting down. They are moving. They are displacing with respect to mean position. But the energy propagation is not happening because physical matter is propagating from this point to this point. It's happening because a disturbance is traveling such that the medium particles are not moving from the source point of the disturbance to the receiving point of the disturbance. So any phenomena like this, however abstract, this is not something which you would relate to our general wave mechanics. But in general manner of speaking, this also comes in the category of wave phenomena. Okay. Now talking about wave phenomena or waves, depending on what type of energy is getting propagated, we divide it into mechanical waves, versus electromagnetic waves. Okay, and as we were discussing earlier, there's an entire electromagnetic spectrum. It's from radio waves to all the way to gamma radiation. And we will talk about this at a later stage also. Visible light comes somewhere in between here. There's microwaves, there's X-rays, all this. But more importantly, in electromagnetic waves, it is electromagnetic energy, okay, which propagates through oscillating electric and magnetic fields. So in a sense, you will also understand more about this after you know about magnetism and about electromagnetic induction also. So become an integral part of understanding electromagnetic waves. So importantly, there is no material medium needed for electromagnetic waves to propagate. Okay. Whereas what we are going to study here in this chapter is mechanical waves. Okay. Now, mechanical waves are waves in which the normal examples are sound, vibrations on a string, etc. So in this case, what happens is there is mechanical energy, which is in the form of kinetic energy and elastic potential energy, or stress and strain energy of a physical medium, okay, which propagates through oscillation of medium particles. Okay. However, the medium particles, okay, do not displace continuously. They have more or less fixed mean positions, but the energy continuously displaces. So that is the difference between wave phenomena and particle phenomena. So this is the demarcation between mechanical waves and electromagnetic waves, which is the first level of classification we'll do of wave phenomena. So I'll just leave you with a bit of time to absorb this information, and then we will come straight to the point, which will be the beginning of our study of mechanical waves. So just make a note of this, people. Okay, so hope this part was clear, people. Now moving on to, so from this point onwards, we are dealing with mechanical waves. Now we'll see further. Mechanical waves can be classified into two categories: transverse and longitudinal waves, as you know. So mechanical waves are of two categories: transverse and longitudinal. So what happens in transverse waves, transverse mechanical waves, is that medium particles displace, or you can say oscillate, such that their axis of displacement or the axis of movement from mean position is perpendicular, or what in the language of waves we call transverse, with respect to the axis of energy propagation. Or what again in the language of waves we call the wave propagation. And the examples of this are vibrations of a string. So as a string vibrates, its shape continuously changes like this. So the energy propagation or the wave disturbance is happening in this. This is the axis of propagation, the disturbance or the wave or the energy of the wave. But the medium particles are not moving like that. The medium particles are just oscillating to and fro about their mean position. So this is the axis of oscillation or displacement of any section, you can say, of the string. So over here we'll treat the section of the string like a particle of the string, which is the medium in which the oscillation is happening. Okay. So this is the definition of transverse mechanical waves, and this is how I explained the example functions for a transverse mechanical wave. Okay, people. So you can understand here that as a string vibrates, if you just keep your eyes fixed on any section of the string, you'll see that that section is only going up and down. It's not vibrating along the axis of propagation. So that's what we mean by transverse mechanical wave. Okay, another example of transverse mechanical waves is ocean waves or the waves on a surface of liquid. Waves on the surface of a liquid. So if you see the top view, this is a calm surface. Now what we do is you create some disturbance. So you see that disturbance, it travels like circular wavefronts, like you drop a stone or something. You see these are traveling outwards. So you see circular wavefronts traveling tangential to the surface of the liquid. So a stone drop onto calm surface pond or tank or something like that. So you see circular wavefronts travel radially outwards along the surface. That means that the propagation of energy is happening tangential to the surface. Propagation of the wave or energy is tangential to the surface. But the water molecules at the surface, you see they kind of bobble, oscillate vertically or normal to the surface. That's why it's an example of transverse. Okay, so that's how this constitutes another example of transverse oscillations or transverse wave phenomenon. Whereas next up we will see that longitudinal wave phenomenon, on the other hand, involves a situation where the medium particles are oscillating along the same axis as the propagation of energy. Okay, so hope this example is clear. Now from this, next thing we'll see is the second type of waves, which are called longitudinal mechanical waves. Okay. So this is a situation where mechanical energy propagates through a material medium by oscillation of the medium particles, but they have a fixed mean position. wherein the axis of motion for oscillation is along the axis of energy propagation or wave propagation. So the physical example of this is basically sound waves. For example, if you consider one-dimensional sound waves, that is sound in air pipe kind of. You understand what happens over here. We create a very long pipe. Infinity on this side. But here we have a source of sound, like a tuning fork. So this tuning fork, it vibrates back and forth like this. As it vibrates back and forth, it creates oscillations like this. So if this is the direction of propagation, and we are taking this as our x-axis, then the oscillations are also along the x-axis, as is the propagation of energy. That's how this constitutes an example of longitudinal waves. Okay. So now let us move more towards the mathematical side of this. So we come to first chapter of waves, which is so coming back to transverse mechanical waves. So we saw two examples of this earlier: vibrations on a string and also the waves on the surface of a liquid. Now, in our particular chapter of study, we will be studying transverse mechanical waves as vibrations or waves propagating along a stretched wire. So thereby these will constitute what we call one-dimensional transverse waves, because the energy is propagating, energy or wave is propagating along a straight line, which is basically the stretch. Hence the term one dimension. So our physical model of this is that you have literally an infinitely long very long straight stretched string, and one end of the string, we take this as the x-axis. This end of the string is the origin, and any general point on the string is our x-equals. So now we see that if we give some kind of a disturbance at the origin, then eventually that disturbance, it travels along this. So that disturbance will be defined by the displacement along the y-axis. So any transverse disturbance or wave phenomena be represented by a displacement along the y-axis, and this transverse displacement, it travels along the x-axis with time. So therefore, the mathematical representation is that we are going to use a function such that y will be defined as some kind of function of x. So the transverse wave or disturbance travels along the x-axis with time. That is why y is going to be a function of x. And we'll see that there are certain types of functions only which can qualify. Not any and every general two-valued functions. Certain types of functions which will qualify to represent this kind of phenomena, which is a one-dimensional transverse wave. Okay, so next we will look more closely at what kind of mathematical functions can be used to represent this kind of traveling wave phenomena. So the oscillation is along the y-axis, Aditya, and the propagation is happening along the x-axis. Okay. So now we will understand how to construct these type of functions. So for a bit of time, we will work on our understanding of functions, two-value functions, and then come back to how they can be used to represent waves. So let us look at about functions, okay, transformations, and waves. Let's understand about this stuff. So, for example, we have the function, suppose y is equal to, let's say, 4 minus x square. Okay. We know the graph of this function. It looks like an inverted parabola. With a peak like this. It looks something like this. Something like this it looks like. Now, let us transform this function to y equal to 4 minus x minus 1 whole square. And what happens over here? Here, the maximum value of y, which is 4, occurs at x equal to 1. Whereas here, what was happening was y maximum equal to 4 occurred at x equal to 0. Here it occurs at x equal to 1. So you can see that what happens in this case is that this whole function it shifts like this. Shifts by 1. Like this. This point goes to plus 3. This point goes to minus 1. So the whole function shifts by 1. So this is not just about this function, this is a general secret. So you see that if we have any function y is equal to fx and its graph looks anything like this, let's say. Then if we transform it to y is equal to f of x minus e, then the whole function shifts like this. It shifts by e units along the positive x direction. Or if we transform it, let's say to y is equal to f of x plus b, then it shifts towards the left. Shifts towards left of this. So this is about transformation of graphs along the x-axis. X is replaced with x minus a for along positive x-axis, and x can be replaced with x plus some constant for transformation along negative x-axis. That's a general. Okay. So let's, for example, just apply this concept here. Look at a function like this. We have y is equal to e raised power minus x square versus y is equal to e raised power minus of x minus 2 whole square. plot the two graphs and compare to understand the transformation of one to the other. Let's try this out, people. So hopefully you had understood that the e raised power minus x square graph actually exponential pulse. If you just use the method of graphical analysis, you'll be able to construct this. It's very easy to construct from basics actually. So if you look at the graph of y is equal to e raised power x, you know that that graph looks something like this. Something like this. So this point here is 0, 1. Similarly, if you look at the graph of y is equal to e raised power minus x, that looks like a mirror image of that. Like this. 0. This point over here. So now if you look at the graph of, for example, e raised power minus of mod x. So what will that look like? So let me take the cube from this graph here. See how the positive side looks, and then draw a mirror image of it on the negative side. Something like this. Peak ends. So from this now you can get an idea of what the graph of e raised power minus x square should look like. Only it looks like a curve at the top now instead of, because it's not a non-differentiable point, now becomes a differentiable point. So it peaks at 0, 1. This is the graph of y is e raised power minus x. Now in comparison to that, if you draw the graph of y is equal to e raised power minus x minus 2 whole square, you will see that this will have a peak at x equal to 2. This peaks at x equal to 0. But rest the shape of the graph is the same. So that's how you understand how the transformation has occurred. So this graph now will be something like this. peak point here is 2, 1. So in comparison to the earlier graph, it's the same shape, but it's got transformed by a shift towards this direction of 2 units. So you can see that this to this is a shift or transformation by plus 2 units on the x-axis. Now similarly, if we look at the graph of these two functions, y equal to sine of x versus y equal to sine of x minus pi by 6. See what the contrast between these is. All these things that we are learning about transformation of graphs are very essential to the understanding of waves, because we'll be representing different kinds of waves with similar kind of functions. So this is not just an arbitrary mathematical exercise. It's actually something that will help us in our understanding of waves. Okay, so you understand here. Our regular sine function is something like this. something like this. This is y is equal to sine x. So you can see that it's peaking off at +1 at x equal to pi by 2. And similarly, 3 pi by 2. So the value -1. Now we can also see here that the value pi by 3 will give it the value of 0.5. So pi by 6 will give it the value of 0.5. So in comparison, this will look like this. This is what the graph of sine of x minus pi by 6. It will be 0 at the point pi by 6. It will reach the peak point at pi by 2 plus pi by 6. That is pi by 3. And similarly, this point here will be pi by 6. But it reaches -1. You can see that it has shifted like this by pi by 6. It has shifted by pi by 6. So now the thing is that these were examples of mathematical functions. So note, in a mathematical function, y is equal to fx, where x and y are numbers, the real numbers. Replacing x with x plus or minus e, where e is also a constant but a number, transforms along the x-axis. But in a physics equation, where y and x are positions or displacements in meters or centimeters or something like that, the function will always be of this type. The argument of the function, what we apply the function to, should be a dimensionless quantity. The argument of the function must be dimensionless, or y must be f of some argument theta, where theta is given such that a is having the dimension of length inverse, so that ax is dimensionless. A is a constant. So for example, we can have a function like y is equal to a into e raised power minus px square, where e is a constant in, let's say, millimeters. Therefore, y is in millimeters, and e is a constant in, let's say, meter inverse. So x is in meters. Okay. Or you can have an example where y is e sine px. This will make sense dimensionally. So e has the dimension of length. E has the dimension of length inverse, the constants. So y is a displacement, x is a position. But this is a function of the type y is equal to some constant into sine theta. This theta is the argument of the sine function, which must be dimensionless. So that's a distinction between a physics type of equation versus a mathematical type of equation. In a physics equation, if x is representing a position or a displacement, then we cannot operate x directly on the function. The function has to be operated on an argument which is dimensionless. We'll have to multiply x with some appropriate constant, even if its numerical value is unity 1. But still, x will have to be multiplied with a physical constant, which makes it dimensionless. Okay. So in that regard now, so we have some kind of a function like this. Y is f of px. Now if we transform this to y is equal to f of p into x minus delta x, then what happens is that the graph shifts, or the graph is shifting by positive delta x along the x-axis. So for example, we have the function y is equal to e sine px, and that is just like the graph we saw. So this is the graph we just saw. Like this, y is varying between plus a and minus a. Now we transform this to y is equal to a times sine of a into x minus delta x. ये पूरा ग्राफ अब कैसे ट्रांसफॉर्म होगा? It shift by delta x. This is the graph of this. Whereas this was the graph of these. This is how transformation applies to the physical equation instead of mathematical equations. Functions where x and y are physical quantities instead of just numbers. So I'll just leave you to write down this part. Understand this in detail. Okay, so that is the important thing. The function's argument has to be dimensionless, like in these functions below. So then the transformation works in this way that when you multiply, when you replace x with x minus delta x or x plus delta x, it shifts along the x-axis such that the argument of the function changes from kx to k of x plus delta x or x minus delta x, like that. So this becomes something important to understand here. Okay, so now from this transformation, we move on to a moving function. So next thing we understand that if we have a function y is equal to f of k into x minus vt, okay, where t is time and v is a constant which has dimension of lt minus 1. Okay. So then what is happening? This is a function. This represents a traveling function, okay, or shape, because what is happening here is that y is becoming a function of x and t such that the shape of the graph does not shift. Only the position shifts with time along the x-axis at a constant velocity v. Because you can understand this by transformation. So for example, if we have the graph of, let's say, 5 e raised power minus of 2x minus 5t whole square, okay, where that 5 or that y is in millimeters, y is in millimeters, x is in meters, let's say, and t is in seconds. Okay. Now, when we plot this graph, you can see that if we plot it at different times, it will represent a traveling pulse shape. Suppose you want to plot y versus x at t equal to 0, then t equal to, let's say, 2 seconds, then t equal to, let's say, 10 seconds, and at a general time t. Okay. So we do that, we will understand how this represents a traveling pulse. Just try this out, people. Right. So if you plot this graph, you will see that we have this function y is equal to 2 into e raised power minus of 2x minus 5t, I think it was, whole square. So now we want to plot it at p equal to 0. So it becomes 2 e raised power minus 4x. Okay. Then we want to plot it at p equal to 2 seconds. It becomes 2x minus 10 whole square. Okay. So you can see that is that exponential pulse kind of graph that we had seen. But at t equal to 0, the pulse's peak is at the origin. So at t equal to 0, we can see that the pulse's peak is equal to 2. The peak is at x equal to 0, y equal to 2. But what happens at 2 seconds or at 2 seconds is that the peak shifts to where this becomes 0. So x is equal to 5 meters, y equal to 2, because this amplitude E is 2 millimeters. This one. Okay, so this has shifted like this to x equal to 5. This is where it is at t equal to 2 seconds. This is where it was at t equal to 0. Now like that, if you were to plot it at t equal to 10 seconds, you would see this has become 2 into e raised power minus of 2x minus 50 whole square. So its peak has shifted to the point where x is such that 2x minus 50 is 0. So x is 25 meters and y is equal to 2 meters. Okay. So it shifted like this. So by now, it has shifted to 25 meters, much further down the line. This compared to this. And in general, at any time t, its peak would be somewhere here. This point would be where x is equal to, at any general time t, it would be such that this argument is 0. So it would be 5 by 2. So you can see that this is traveling. The peak has shifted from 0 to 5 by 2 t in t seconds. So it's traveling with the speed of 5 by 2 meters per second. So this is how it represents a traveling pulse. Let's look at another example to understand this thing. But before that, we can see that a function of this type or basically this is a function of this type argument of the function is kx minus some constant into t, or you can write that as k into x minus vt. Okay, where if you connect these two, you can see that omega, which is k constant, okay, the dimension of omega is time inverse because k has dimension m. So you can see that this kind of function, it now represents a traveling one-dimensional disturbance or wave, where y is the transverse displacement of a point on the x-axis at an instant, that is t equal to t. But it is such that the disturbance or wave is traveling at a uniform speed v equal to omega by k along positive x-axis. Okay. That is the function kx minus omega t, because the argument of that function kx minus omega t can also be interpreted as k of x minus bt, where k into v is omega, or v is omega by k. Okay, so that is why v becomes omega by k, and when this sign is minus, it's traveling along the positive x direction because it's transforming in this way. Okay. So in this particular example, this function was that exponential function. So this particular example of this function, it is called the exponential traveling pulse. Okay. It is an example of 1D transverse wave. One example of it. The more general thing is this. This becomes the general equation. This here becomes the general equation which represents this thing. So it depends on x and t in this case. people, hope all this is clear. If there is any doubt, please ask me. So this type of equation becomes a general equation for a one-dimensional transverse wave or disturbance, and it's traveling along the positive x direction if the sign is minus. Okay. Also, we can see one thing, that if we replace the minus sign in between the two variables kx and omega t with a plus sign like this, then this is traveling along the negative x direction at a speed v equal to omega by k. The magnitude of the velocity is still omega by k, but the direction becomes along the negative x direction, because it, when you replace x with x plus delta x, the graph shifts towards the negative x direction. When you replace it with x minus delta x, it's transforming along the positive x direction. So hence the difference of sign makes the difference of the direction of propagation. Okay. Now further we will see something important here, that while this is a general equation where we can fit any function, but the function may be like that exponential pulse which you are seeing, in which case it is now, suppose the function is what we call non-periodic function. It doesn't repeat itself. Okay. An example of that was the exponential pulse that we just saw. This kind of function. So the function is non-periodic. Then y represents what we call a traveling pulse. Okay. And that you understood from how the graph was shifting. So it becomes a shape like a pulse, like this, which is shifting along the positive or negative direction. It's a single pulse. Okay. Whereas on the other hand, if the function happens to be a periodic function, like this next example I'm going to demonstrate. The function happens to be periodic. For example, y could be some amplitude into sine square for that matter, kx minus omega t. Now this would represent what is called a periodic wave. So this would represent a situation where the shape of the medium is periodic in nature. The shape of the string is like this, like a sine square function here, and this whole thing is shifting with time. This whole thing is continuously shifting with time. Okay. So a periodic wave involves such a thing that the medium particles oscillate with definite amplitude and time period. Whereas in the case of a traveling pulse, the medium particles do not continuously oscillate. Instead, as the pulse passes through a certain region of the medium, or certain point in the string in this case, the particles have a one-time displacement to a maximum amplitude and they come back. So as the pulse travels through point in the medium, a point will be designated by a certain x coordinate. It makes a maximum displacement and then returns back to y equal to 0 position. Okay. So it's like a one-time movement, not a continuous oscillation for medium particles. Hence, there is no such thing as time period or amplitude for that matter. There's a maximum displacement and it comes back. Whereas in this case, there's a continuous oscillation happening at a fixed time period. Okay, so that is the difference between a continuous traveling wave and a single pulse which is traveling. But both come under the category of transverse disturbance or transverse waves. Okay, so to understand this difference between traveling pulse and continuous wave, we've already seen the example of traveling pulse earlier. Now let's look more closely at the example of continuous wave. Okay, so let's look at all these aspects for this particular question. So this time, again, it is, you can see it is the general form of the wave equation, but the function itself is which function? It's the cos function. This of the type f of ax plus or minus omega t. But this function is this time which function? It is a cos theta 10, where theta is ax minus omega t. So it's a periodic function. Hence, you will see that it is a continuous periodic wave, and that will reflect in both these parts when you work them out. Okay, so let's start with the plot of y versus x at these various times. So we had this function 4 cos pi by 10 and 20 pi. So this function y is 4 cos pi by 10x minus 20 pi t. Now we wanted to plot the first part y versus x at t equal to 0. So that was simply the 4 cos pi by 10x graph. So this would look like a regular cos graph. Looks like a regular cos graph, something like this, but more symmetrical. So let's try it once more. Like this, you can see. So this is our y versus x graph at t equal to 0, where x is in meters, y was in millimeters. Y is ranging between this maximum value on the positive side, which is plus 4 millimeters, and on the negative side, which is minus 4 millimeters. Also, we'll see that this point is where this term will become pi by 2. So it should be x equal to 5. This point is where it should become pi. So it should be 10. Similarly, this point is 15. This point is 10. Okay. Now, if we compare this with, okay, this is what this looked like at t equal to 0. Now, if we compare this with the b part, this where we are plotting y at t equal to, I think it was 25 milliseconds. So you'll see that at t equal to 25 milliseconds, what will happen is in our original function, this term, the b part, t equal to 25 milliseconds में जो omega t वाला term है, वो क्या हो जाएगा? It will become 20 pi into 25 milliseconds. So that's 25 by 1000. That's 500 by 1000 pi, or it will become pi by 2. Okay, so this graph, which is of the type e cos kx minus omega t. So at the instant t equal to 25 milliseconds, the omega t term will become pi by 2. Okay. So this graph will actually become four cos kx, which is pi by 10t. So pi by 10x minus that omega into 25 millisecond term, which is becoming pi by 2. Okay. So that will actually become the sine graph. This graph will become equivalent to sine pi by 10, pi by 10x. Okay. So you can see that the shape of this graph would have shifted from this to the sine curve. This is how this whole thing is looking at t equal to 25 milliseconds. You can see the graph is shifting like this, and you would see that it will be like this. To 25. So this is how the graph is transforming with time. Like that, you can try the C part yourself. C part, you have to plot y at t equal to 50 milliseconds. So this, see how that works out. Okay, so you will see that for the C part, at this time of 50 milliseconds, this omega t term, 20 pi into 50 milliseconds, will become pi. Okay. So this will become 4 cos pi by 10x minus pi. So that will become minus 4 cos pi by 10x. In the same graph, now if we want to overlap the shape of the medium, at the instant, this one, the C part, t equal to 50 milliseconds, we'll see that this becomes the minus e cos px kind of graph, because that term becomes pi. So it becomes graph here which will look like this. So again, you can see the graph is shifted. So the shape of this thing always remains in general like a sine curve. Cos curve and sine curve have the same shape, but it keeps transforming along the x-axis at a constant rate, and that speed with which it's transforming will be our omega by q. So this equation y is equal to e cos px minus omega t. This is the shape is cos or sine curve, which shifts along or propagates along the positive x-axis at v equal to omega by q, which you will see is over here. Omega was 20 pi and k was pi by 10, so 200 meters per second. And that you will understand here also, because you can see that in 25 milliseconds it has shifted by, you can see this peak point is shifted from 0 to 5, then 5 to 10. So, or you can see that V is delta x by delta t. Each of those peaks or troughs are shifting by 5 meters in a matter of 25 milliseconds. So that is 5 by 25 into 1000 meters per second. That's the same thing as 200 meters per second. So the graph is also giving you the same information about how the transformation or the continuous shift of the shape is happening. Okay, so this is the answer to the first part, E part. And in this you can also see that the maximum wide displacement is equal to E, which is in this case. Okay, so this is about the first part. Just a second, people. I will reshare the whiteboard. Just a second. Okay. Now, on the other hand, when we look at the second part of this same example, we are looking at plotting, instead of y as a function of x, we are looking at plotting y as a function of time for the value x equal to 0 or x equal to 5 or x equal to 10. The second part, this function where its amplitude was 4 millimeters, the value of k was 5 by 10 and x was in meters, so this is in radians per meter, and the value of omega was 20 pi and time was in seconds, so this is in radians per second. Now we want to plot y as a function of t for x equal to 0. So that is becoming e cos minus omega t, or that's the same thing as e cos omega t. In this case, that is 4 cos 20 pi t. So we can see that this is an SHM, where y naught is equal to plus 4, amplitude is equal to 4, omega is equal to 20 pi. So time period is equal to 0.1 seconds, or frequency is equal to 10 hertz. So we can see that the particle located at x equal to 0 is an SHM with these properties. So this is y versus t for that particular particle which is located at the position x equal to 0 on the x-axis. So we can see that that is doing this kind of oscillation with an amplitude of 4 millimeters and the time period like this. So y equal to 4 cos 20 pi t. This becomes the equation of SHM for the particle located at x equal to 0. This is SHM of the particle at x equal to 0. But the SHM is of course happening along the y-axis. Now we compare this to the point x equal to, we taken 5 and 10 meters. So if we now plug in the value 5 meters over here, so this kx term will become pi by 2. So for x equal to 5 meters, this will become e sine k, which was pi by 10 into x, which is 5 minus 20 pi. So this will become, so e cos, become e cos pi by 2 minus 20 pi t. So this equation will now become 4 sine 20 pi t. So this is the equation of SHM. This is SHM along the y-axis for the medium particle at x equal to 5 meters. It has an amplitude of 4 millimeters and again a time period of 0.1 seconds, or omega equal to 25. So this one's oscillation with respect to time looks like a regular sine graph. So this is one time period. Or over here, this will be the completion of one cycle. This will be half a cycle. This will be quarter of a cycle. And that time period is 0.1 seconds. Okay. And similarly, if you were to look at the time, sorry, the position at x equal to 10 meters. See, it will become 4 cos pi by 10, that is kx, which is 10, minus omega. So it will become minus a cos omega. Right? This kind of function. Because this is 4 cos pi minus omega. Okay, so pi minus omega t becomes minus cos. So this is the SHM of the particle at x equal to 10 meters. So you can see that, therefore, finally what's happening, all 3 particles in this, which we have considered, x equal to 0, x equal to 5 meters, and x equal to 10 meters, are in SHM with an amplitude of 4 millimeters and a time period of 0.5 seconds, or frequency of 10 hertz. Okay. But x equal to 0 and x equal to 5 have pi by 2 phase difference, because this one was e cos omega t and this one was e sin omega t. And in comparison, x equal to 0 and x equal to 10 have a phase difference of pi. Okay. Because this one was e cos omega t and this one is minus a cos omega t. Okay. Now this factor, these two things, this is also seen in the graphs of y versus x at various times. You will see that these two particles, the ones at 0 and 5, they are a pair which are at pi by 2 phase difference in their oscillation. Whereas if you compare 0 and 10, they are at a phase difference of pi. If you go back to these graphs earlier, this one, now you can see जो particle 0 पे है और जो particle 5 पे है, see how they are oscillating in comparison. They are oscillating with pi by 2 का phase difference, because at the initial time This one is at amplitude, this one is at the mean position. Then quarter of a cycle later, okay, what happens is that this one comes to the mean position, but now this one has progressed to the positive extreme. Then quarter of a cycle later, how I know it's quarter of a cycle, because I've seen the time period was uh, 0.1 seconds or 100 milliseconds, and here it is 25 milliseconds, that's quarter of a time period, and this is 50, that's half a time period. So you can see that this is going from plus a to 0. In that time, this is going from 0 to plus a. Then this is going from 0 to minus a. In that time, this is going from plus a back to 0. Like that, if you notice the particle at 0 and the particle at 10, they are having pi phase difference, because initially this was at positive amplitude, this is at negative amplitude. Then they cross the mean position together, but this is on the way up, this is on the way down. So these two particles are always oscillating. The pair 0 and 10, they are oscillating with pi phase difference, whereas 0 and 5, they are oscillating with a phase difference of pi by 2. And similarly, you notice the particles located at 0 and 20, they are oscillating in phase. In fact, any two particles separated by 20 meters in this case are oscillating in phase, which is why we'll see later that we'll define 20 meters as the wavelength. It is the shortest distance between points oscillating in phase. Okay. So anyhow, just first make a note of this thing. Okay, people, so hope this part is clear. Okay, so through these two examples, the exponential pulse example and the example of the sinusoidal shape, if we wrote in terms of a cos function, but you know that a cos function and a sine function have the same shape like you've seen in SHM. You only have a phase difference of pi by 2. So we have understood the difference between a continuous traveling wave, which creates oscillation for the medium particles, versus a traveling pulse, which creates a one-time kind of motion from 0 to maximum and back. So this concludes our first lecture of waves. You can start reading part of the chapter from H.C. Verma, the mechanical waves, vibrations on a stretch string, the first chapter of wave mechanics, which is to do with transverse waves actually. And next time we'll be discussing sinusoidal waves in more detail, but we'll also look at general equation once more and few more examples of this. And we will start looking at the exact formula and relationship between things like, you know, the constant k and the wave number or the wavelength lambda. Similarly, the constant omega and the frequency f or time period, they have a particular relationship. And similarly, the wave propagation velocity has a relationship which we've already seen omega by k, but that also becomes f lambda. So we will see these particular relationships. We'll also discuss about power transmitted through a wave and things like that. So that's it for today's lecture. Now in this remaining, I mean, from tomorrow onwards, I guess what you have to concentrate more is the preparation for the upcoming test on 10th, on 28th. So for that, make sure that you do a thorough revision of geometrical optics along with, of course, electrostatics and capacitors and all those things. Geometrical optics pay particular importance to the questions we did in the last couple of classes, including combination of lenses in contact and thin lens in contact with the mirror, the equivalent formula from that, and of course the prism analysis part, and thin prisms, and also the case of the dispersion, the angular dispersion and dispersive power and those particular formulae, and of course optical instruments, the compound microscope and things like that. But remember, optical instruments is only for JEE mains, whereas the other things are for both mains and advanced. Okay. So that's it for today's class, people. All the best and work hard for the upcoming test, and any doubts, etc., you can discuss with me.